Hello, folks, and welcome back to my stream. I have been dealing with the Airtel Wi Fi issues, so it has been some delay from them to get this up and working again. And today I am back with the Crosslingual Emergent Misalignment Mechanistic Interpretability project that project that we have been working on, and we will be exploring some notebooks and doing research live and going through the activation extraction, then the EM direction, cosine similarity, ABTT corrected cosines, RSA cross-lingual geometry, robustness and sensitivity checks, and then for the new direction that I am pursuing, the cross-lingual activation patching, and a couple of more steps. So right now what I'm doing is I have been using a Lambda instance of, you can see the server here, the NVIDIA A100 SXM4 40 GB. I couldn't get the this server that I was looking for, NVIDIA A6000, the 48 GB one that had $1.09 per hour. Currently, I'm using this guy here that has $1.99 per hour, and it is on SXM4. And like I had a chat with the good folks at Lambda, and they said that this isn't available right now, so they will be providing access to NVIDIA A6000 as soon as it is available. This is the instance. Yeah, this is the query that I made. They said that on US South 2 it will be available, or US South 1. Since it is in transition, therefore these instances are unavailable. So that's why. Anyways, let's get back to the activation caching, which, so this, these are the tasks that I have been doing. I've set Droid up, I have added MCPs, UV installed, and all the files synced. Then for this pipeline, I have been doing uh, tuning for the batch size such that full 40 gigs of VRAM is being utilized. But currently, after that, it's throwing a OOM, and uh, now it accounts for the logit's tensor in the BF6 96 MB per sample, which was the dominant cost of the previous estimate completely missed. So, uh, with the 60% safety margins, the computed batch size is clamped to 16, down from 64, and this has been wrapped in the recursive underscore run underscore sub underscore batch helper that caches torch.cuda.out of memory error, halves the batch, clears the cache, and retries. This ensures the extraction always completes even if the particular batch has usually long sequences. So after this, I think so. This should let me try to fix. Okay, and there was some remaining instances I need to. Sorry, some remaining processes that had some memory usage which I needed to clear up. So I restarted the notebook. So the config's completed. Let me do that again by deleting the caches. And it 384 items in 8.3 seconds. Done with the extraction. So to clear this guy here, what I will have to do is restart this notebook once, and this will be cleared. The Jupyter kernel, which see it has been cleared now. Going to the layer wise cosine similarity. So these were the figures that I had generated earlier. Let's regenerate them. think we need to update this interpretation guide. So let me, because with the crosslingual similarity, for the 03 underscore layerwise underscore cosine underscore similarity dot ipynb, could you update the interpretation guide which takes into account the numbers which you have shown in the figure and the logs above, the results above, and make it so that you have the theoretical as well as the empirical evidence to support your hypothesis and the interpretation. I think so. I will have to do the same for the 04 EM direction alignment notebook. So let's try that. Could you do the same for the 04 EM direction alignment not IPYNB notebook with respect to updating the interpretation guide, which takes into account the numbers which you have shown in the figures and logs from the above results, and make it so that you have the theoretical as well as the empirical evidence to support your hypothesis and interpretation. I have redone the notebook, so some of the empirical observations might be changed here. Could you verify the markdown of these changes from the results and the figures above? So, on my other monitor, I have been running the uh, Dylan Patel podcast, and yeah, this is what I'm doing in parallel right now. Let me.
Power, et cetera, of these chips. But it's also unlikely to some extent, to a large extent, because of I think just comparing, some of these are like not fair comparisons, right? For example, from A100, which is 312 teraflops, to Blackwell, which is like 1,000 ish of FP16, or maybe it's 2,000, and then Rubin is like 5,000 or so FP16. It's not a fair comparison because these chips have vastly different design targets, right? At A100, that is what NVIDIA optimized for, was FP16, bfloat16 numerics. When you look at Hopper, they didn't care as much about that. They cared about FP8. When you look at Rubin, they don't care about FP16 and BF16 as much. They care mostly about FP4 and 6, right? And so numerics are what they've designed designed their chip for. And so there's a couple okay, let's redesign, let's make a new chip design on 7 nanometers. Sure, we can do that. And then it's optimized for the numerics of the modern day. The performance difference is still going to be much larger than the flops difference you mentioned, right? Often it's easy to boil things down to flops per watt or flops per dollar, but that's actually not a fair comparison, right? And so this is where sort of you can bring in, hey, let's look at Kimi K1 or DeepSeek. When you look at Kimi or Kimi K2.5, sorry, and DeepSeek, when you look at these two models and you look at their performance on Hopper versus Blackwell on very optimized software, you get vastly different performance, right? And most of this is not attributed to flops. A lot of this is or numerics, right? Because those models are actually 8-bit. So it's not like Blackwell's and Hopper, they're both optimized for 8-bit, and Blackwell's not really taking advantage of its 4-bit there. The performance gulf is actually much larger. And the way you can sort of compare them and think about them is, sure, it's one thing to shrink process technology and make the transistors smaller, and each chip has X number of flops. But you forget the big gating factors is these models don't run on a single chip. They run on hundreds of chips at a time, right? If you look at DeepSeek's production deployment, which is well over a year old now, they were running on 160 GPUs, right? And that's what they serve production traffic on. And so they split the model across 160 GPUs. Every time you cross the barrier of a chip to another chip, there is an efficiency loss because you now have to transmit over, high-speed electrical SerDes, and there's a latency cost, there's a power cost, there's all these dynamics that hurt. As you shrink and shrink and shrink the process node, you've increased the amount of compute in a single chip. Now, in-chip, right, movement of data is, at hundreds or of at least tens of terabytes a second, if not hundreds of terabytes a second. Whereas between chips, you're on the order of a terabytes a second, right? And so this movement of data between chips that are super close to each other physically, and then you can only put so many chips close to each other physically, so you have to put chips in different racks. The order of data between that is on the order of hundreds of gigabits a second, right? 400 gig or 800 gig a second. So 100 gigabytes a second roughly. And so you've got this like huge ladder of like, on chip I can communicate at super fast speeds. Within the rack I can communicate at order of magnitude speeds. Outside the rack I can communicate at an even order of magnitude lower than that. And as you break the bounds of chips, you end up with this performance loss. So anyways, the reason I explain this is because when you look at Hopper versus Blackwell, even if both of them are using, a rack worth of chips, the Hopper is significantly slower because the amount of performance that you have leveraged to the task within that, within each domain of, hey, tens of terabytes a second of communication between these transistors or these processing elements, and, terabytes a second between these processing elements is much, much higher, and therefore the performance is much higher. So when you look at inference at, let's say, 100 tokens a second for DeepSeek and Kimi K2.5, Hopper versus Blackwell, the performance difference is on the order of 20x.
Interesting.
Not 2 or 3x like the flops performance difference indicates, even though those are on the same process node.
Makes sense, yeah.
There's just differences in networking technologies and what they've worked on. And so you can translate some of these back. But when you look at like Rubin, what they're doing on 3 nanometers, some of these things are just not possible to do all the way back on A100, even if you make a new chip for 7 nanometer. There's just like certain architectural improvements you can port. There's certain ones you cannot. And so the performance difference is not just going to be the difference in flops. It's in some senses cumulative between the difference in, flops per chip, networking speed between chips, how many flops are on a chip versus a system, memory bandwidth on a single chip and on an entire system. All of these things compound.
Can I ask you a very naive question? So last year, the B200 has now 2 dies on a single chip, so you can get that bandwidth on a single chip without having to go through NVLink or InfiniBand. And then next year, Rubin Ultra will have 4 dies on one chip. What is preventing us from just doing that with an old, like how many dies could you have on a single chip and still get these tens of terabytes a second?
Yeah, so even within Blackwell, there are differences in performance when you're communicating on the chip versus across the chips. Those bounds are obviously much smaller than when you're going, out of the entire chip, but each die versus, within the package. And so anyways, when you scale, the number of chips up, there is some performance loss. It's not just perfect, but it is way better than different entire packages. Now, how large can advanced packaging scale? The way NVIDIA's doing it is CoWoS, the way, Google and with Broadcom and MediaTek and, Amazon, Trainium, all these chips are doing is called CoWoS. But actually, you can go and look back at what Tesla did with Dojo, right? Dojo, which they canceled and restarted. I don't know. Anyways, Dojo was a chip that was the size of an entire wafer. They had 25 chips on it. And there were some trade-offs, right? They couldn't put HBM on it. But the positive side was that they had 25 chips on it. And so to date, it is still probably the best chip for running convolutional neural networks. It's just not great at transformers because the sort of the shape of the chip, the memory, the arithmetic, all these various specifications of it are just not well suited for transformers. They're well suited for CNNs. And anyway, so Dojo chips were optimized around that. They made a bigger package, but at the same time, as you make packages bigger and bigger and bigger, you have other constraints, right? Networking speed, memory bandwidth, cooling capabilities, all of these things start to rear their heads. It's not simple, but yes, you will see a trend line of more chips on the package. And yes, you're going to be able to do that on 7 nanometer. In fact, that's what Huawei did with their Ascend 910C or D. They were initially just 1 and then they did 2, and they're focusing on scaling the packaging up because that is an area where they can advance faster than sort of process technology where they can't shrink. But at the end of the day, that's still, that's something that you can do on the leading edge chips too, right? Anything you do on 7 nanometer, you can also probably do on 3 nanometer in terms of packaging.
So if we end up in this world in 2030 where the West has the most advanced process technology, but it has not ramped it up as much, whereas China, I don't know if you think by 2030 they would have EUV and I don't know 2 nanometer or whatever, but they are semiconductor pills, so they are producing in mass quantity. Basically, I'm wondering what the year is where there's a crossover where our advantage in process technology has faded enough and their advantage in scale has increased enough. And also their advantage in like having one country that has the entire supply chain indigenized rather than having random suppliers in Germany and Netherlands and whatever would mean that China would be ahead in its ability to produce mass flops. Yeah,
so to date, China still does not have entire indigenized semiconductor supply chain, right?
But within 2030?
Yeah, by 2030, it's possible that they do. But to date, right, all of China's 7 nanometer and 14 nanometer capacity uses ASML DUV tools, right? and the amount that they can ship and import from ASML is large. And but the point being that the vast majority of ASML's revenue, especially on EUV, all of it is outside of China. So the scale advantage is still in the favor of let's call it the West plus Taiwan, Japan, et cetera.
But they're trying to make their own DUV and EUV tools, right?
They're trying to do all these things. The question is how fast can they advance and scale up production as well as quality. And to date, we haven't seen that. Now, I'm quite bullish that they're going to be able to do these things over the next 5 to 10 years, right? Really scale up production, really kick it into high gear. They have more engineers working on it. They have more desire to throw capital at the
So by
problem.
2030, do they have fully indigenized DUV?
I think for sure.
Okay.
DUV, yes.
And fully indigenized EUV by 2030?
I think they'll have working tools. I don't think that they'll be able to manufacture a bunch yet, right? There's sort of having it work and then there's production hell, right? And ultimately, like ASML had EUV working in the early 2010s at some capacity, right? Now, the tools were not accurate enough. They were not scaled for high production, scaled for high volume manufacturing, reliable enough. And then they had to ramp production, and that all took time. Production hell takes time, right? Which is why it took another 5 to 7 years to get EUV into mass production at a fab rather than just working in the lab.
So how many DUV tools do you think need to be manufactured in 2030?
ASML?
No, China.
Oh, that's a great question. It's a bit of a challenge to look into the supply chain, especially we tried really hard. But in some instances, they're like buying stuff from Japanese vendors, and if they want a fully indigenized supply chain, they need to not buy these lenses or buy these projection optics or stages from Japanese vendors. They need to build it internally. So it's really tough to say where they'll be able to get to. Like, I honestly think it's like a shot in the dark, but it's probably not unlikely that they'll be able to do on the order of 100 DUV tools a year, whereas ASML is doing hundreds of DUV tools a year currently. No one's made a process node. No company has a process node where they make 1 million wafers a month, right? Elon says he wants to do it, and China's obviously going to do it, right? And I don't think TSMC is trying to do that. The memory makers may get there as well, right, to the 1 million wafers a month, but not in a single fab. It's sort of mind-boggling to think of that scale, and challenging to see the supply chain galvanized for that. So I'm not sure, I don't want to doubt, China's capability to scale.
Right. I guess this is an interesting question, and I think it might, at some point, semi-analysis will do the deep dive on this. But I think this question of by when would China be able, indigenized Chinese production could be bigger than the rest of the West combined if you just add up all the and put in the input of your model when they'll have DUV machines at scale, when they'll have UV machines at scale. Because I think there's this question around if you have long timelines on AI, by long meaning 2035, which is not that long in the grand scheme of things. Should you expect a world where China is dominating in semiconductors? Which I think, doesn't get asked enough. In San Francisco, we're just thinking on time scale of weeks. And then if you're outside of San Francisco, you're not thinking about AGI at all. And so this question of okay, what if we have AGI? What if you have this transformational thing that is commanding tens of trillions of dollars or hundreds of trillions of dollars of economic growth and token output and so forth? But then it happens in 2035. And what does that imply for the West versus China? I think it's just the semi-analysis has got to write the definitive model on this.
Yeah, so I think it's really challenging when you move timescales out that far, right? What we tend to focus on is we're tracking every data center, we're tracking every fab, we're tracking all the tools, and we're tracking where they're going, but the time lags for these things are relatively short, right? We can only make reasonably accurate estimates for data center capacity based on, land purchasing and, permits and turbine purchasing and all these things, and we know where all these things are going, and that's what the data we sell is, but as you go out to 2035, things are just so radically different, and your error bars get so large, it's kind of hard to make an estimate. But at the end of the day, there is, if takeoff or timelines are slow enough, right, then certainly China, I don't see why they wouldn't be able to catch up drastically, right? In some sense, we've got this valley, right, of where, call it 3 to 6 months ago, Chinese models were, or maybe even now, Chinese models are competitive as they've ever been. I think Opus 4.6 and GPT 5.4 have really pulled away and made the gap a little bit bigger, but I'm sure, some new Chinese models will come out. But as we move from, hey, these companies are selling tokens where they provide the entire reasoning chain and all that to selling automated, white collar work, right? Automated software engineer, send them the request, they give you the result back, and there's a bunch of thinking on the back end that they don't show you. The ability to distill out of American models into Chinese models will be harder, A. B, as the scale of the compute that the labs have, right? OpenAI exited the year with roughly 2 gigawatts last year. Anthropic will get to 2+ gigawatts this year, and by the end of next year, they'll both be at 10 gigawatts of capacity. China is not scaling their AI lab compute nearly as fast. And so at some point, when you can't distill the learnings from these labs into the Chinese models, plus this compute race that OpenAI, Anthropic, Google, et cetera, Meta are all racing on, at some point they end up getting to a point where the model performance should start to diverge more. And then all of this CapEx that's being spent on, data centers and all that, right? Amazon, 200 billion, Google 180, so on and so forth. All these companies are spending hundreds of billions of dollars of CapEx. There's nearly $1 trillion of CapEx being invested in data centers in America this year, roughly, right? you end up with, okay, well, what's the return on invested capital here? You and I would think that the return on invested capital for data center capex is very high. And at least if we look at Anthropic's revenues in January, they added like 4 billion. In February, which is a shorter month, they added like 6. We'll see what they can do in March and April. Given compute constraints are what's bottlenecking their growth, right? The reliability of cloud code is actually quite low because they're so compute constrained. But if this continues, then the ROIC on these data centers is super high.
Yeah.
And at some point, the U.S. economy starts growing faster and faster over the next, this year and next year because of all this capex and all this revenue that these models are generating, and downstream supply chain. Versus China doesn't have that yet, right? They have not built the scale of infrastructure to then invest in models to get to the capabilities to then deploy these models at such scale, right? Because when you look at like Anthropic's, hey, they're at, call it 20 billion ARR. Of that, the margins are sub 50%, at least last reported by the information. So then, you're at, okay, that's like $13-14 billion of compute that it's running on, rental cost wise, which is actually like $50 billion worth of capex that someone laid out for Anthropic to generate their current revenue. And China has just not done this. If and when Anthropic 10x's revenue again, and I think our answer would be when, not if, then China doesn't have the compute to deploy at that scale. And so there is some sense of like, oh, we're in fast takeoff-ish, right? It's not like we're talking about, Dyson sphere by X date. It's more like the revenue is compounding at such a rate that it does affect the economic growth. And the resources these labs are gathering are going so fast that and China hasn't done that yet. So in that case, the U.S. And the West is actually diverging. The flip side is actually these infrastructure investments have middling returns. Maybe they're not as good as hoped. Maybe Google is wrong for wanting to take free cash flow to zero and spend $300 billion on capex next year. Maybe they're just wrong. And people on Wall Street who are bearish and people who don't understand AI are correct, right? And in which case, then the U.S. is building all this capacity. It doesn't get really great returns, and China is able to build the fully vertical indigenized supply chain, not U.S., Japan, Korea, Taiwan, Southeast Asia, Europe, all these countries together building this like less vertical supply chain. And in a sense, at some point, China is able to scale past us. If AI takes longer to get to certain capability levels, then I would say the vast majority of your guests on this podcast believe.
Yeah. It's like fast timelines, U.S. wins, long timelines, China wins.
Right, but I don't know what fast timelines means, right? Like I don't think you have to believe in AGI to have the timelines where the U.S. wins.
Okay, let's go back to memory, because I think this is maybe people on Wall Street and people in the industry are understanding how big this is, but maybe generally people don't understand how big a deal this is. So we've got this memory crunch, as you're talking about. And earlier I was asking about, could we solve for the EUV tool shortage by going back to 7 nanometers? So let me ask a similar question about memory. HBM is made of DRAM, but has 3 or 4x less bits per wafer area than the DRAM is made out of. Is it possible that accelerators in the future could just use commodity DRAM and not HBM? And so we can make much more capacity out of the DRAM we get. And the reason I think this might be possible is, look, if we're going to have agents that are just going off and doing work and it's not a synchronous chatbot application, then you don't necessarily need extremely high, fast latency kinds of things anymore. And so maybe you can have the low bandwidth, because the reason you stack DRAM into stacks and make HBM is for higher bandwidth. And so is it possible to go to HBM accelerators and basically have the opposite of cloud code fast, like have cloud code slow and and do that?
Yeah, I think at the end of the day, the incremental purchaser who's willing to pay the highest price for tokens also ends up being the one that's like less price sensitive. And the compute should be allocated in a capitalistic society towards the goods that have the highest value, and the private market determines this by willingness to pay. And so to some extent, sure, Anthropic could actually release a slow mode, right? They could release Claude slow mode and have an increase in tokens per dollar by a significant amount. They could probably like reduce the price of Opus 4.6 by 4x, 5x, and reduce the speed by maybe just like 2x. Like the curve on inference throughput versus speed is there already just on HBM. And yet they don't. Because no one actually wants to use a slow model. And furthermore, on these agentic tasks, it's great that the model can run at this time horizon of hours. That's kind of like, okay, well, if the model was just running slower, that hours would become a day, right? Or vice versa, right? If the model's running faster, that hours becomes hour. And yet no one really wants to move to that day-long wait period because the highest value tasks also have some time sensitivity to them, right? And so I struggle to see, yes, you could use DDR, but then there's a couple like things that are challenging with this, right? You could use regular DRAM. One is you're still limited. One of the like core constraints of chips, even though they're sort of like there's a chip is like a certain size. All of the I/O escapes on the edges of the chip, right? So oftentimes, what you see is the left and the right of the chip are HBM. The I/O from the chip to the HBM is on the sides, and then the top and bottom are I/O to other chips, right? And so if you were to change from HBM to DDR, then all of a sudden this I/O on this edge would have significantly less bandwidth, but it had significantly more capacity per chip.
Yeah.
Because and so yes, you're making less. The metric that you actually care about is bandwidth per wafer, not bits per wafer.
Because the thing that is constraining the flops is just getting in and out the next matrix. And for that, you just need more bandwidth.
Yeah, getting out the weights and getting in and out the KV cache.
Right.
And so in many cases, these GPUs are not running at full memory capacity. Yes, it's obviously like a system design thing, model hardware, software co-design of, hey, how much KV cache do I do? How much do I keep on the chip? How much do I offload to other chips and call when I need it for tool calling or whatever? How much do I, how many chips do I parallelize this on? Obviously, these are like, the search space of this is like very broad, which is why we have like Inference X, like this is like an open source model, like searches all the optimal points on inference for a variety of 8 different chips and models. Anyways, like the point is, you're not always necessarily constrained by memory capacity. You can be constrained by flops, you can be constrained by network bandwidth, you can be constrained by memory bandwidth, or you can be constrained by memory capacity. There's sort of like 4, if you're really to simplify it down, there's like 4 constraints, and each of these can break out into more. But in this case, if you switch to DDR, yes, you produce 4x the bits per DRAM wafer, but all of a sudden the constraints shift a lot and your system design shifts a lot. You go slower, yes. Is the market smaller? Okay, maybe, possibly. But also now all of a sudden all these flops are wasted because they're just sitting there waiting for memory. It's like, great, I don't need all that capacity because I can't really increase batch size because then the KV cache is going to take even longer to read.
Makes sense,
and so
Interesting. What is the bandwidth difference between HBM and normal DRAM?
Yeah, so an HBM stack of HBM4, let's just talk about like the stuff that's in Rubin because that's what we've been indexing on, is 2048 bits across, connected in an area that's like 13 millimeters wide. So 2048 bits, and it transfers memory at around 10 gigatransfers a second. So a stack of HBM4 is 2048 bits on an area that's 13 millimeters wide, roughly, or 11. And that's the shoreline that you're taking on the chip. And in that shoreline, you have 2048 bits transferring at 10 gigatransfers per second. You multiply those together and you divide by 8 bits to bytes. You're at roughly 2.5 terabytes a second per HBM stack, right? When you look at DDR, in that same area, it's maybe 64 or 128 bits wide, and that DDR5 is transferring at anywhere from 6.4 gigatransfers a second to maybe 8,000 gigatransfers a second. So your bandwidth is like significantly lower, right? It's 64 times 8,000 divided by 8. You're at 64 gigabytes a second. And even if you take a generous interpretation of 128 times 8 gigatransfers, you're at 128 gigabytes a second for the same shoreline versus 2.5 terabytes a second. There's an order of magnitude difference in bandwidth per edge area. And if your chip is a square, or it's 26 by 33, right, is the maximum size for a chip, individual die, you only have so much edge area. And then on the inside of that chip, you put all your compute. There's things you can do to try and change, right? More SRAM, more caching, blah, blah, blah. But at the end of the day, you're very constrained by bandwidth.
Interesting. So then there's a question of like, where can you destroy demand to free up enough for AI? And I guess the picture is especially bad because, as you're saying, if it takes 4x more wafer area to get the same byte for HBM, you have to destroy 4x as much consumer demand for laptops and phones and whatever in order to free up 1 byte for AI. So, what does this imply for the next year or two of? Sorry for the run-on question. I think on your newsletter you said 30% of the capex in 2026 of big tech is going towards memory.
Yes.
That's insane, right?
Yeah.
Like of the 600 billion or whatever, you're saying 30% is going just to.
And obviously there's some level of like margin stacking that NVIDIA does, and so if you separate out, and you apply their margin to the memory and the logic, but at the end of the day, like a third of their capex is going to memory.
That's crazy. Okay, so what is the question I'm trying to ask? It's something like, what does this imply? What should we expect over the next year or two as this memory crunch hits? Yeah,
so memory crunch will continue to be harder and harder, and prices continue to go up, and this affects different parts of the market differently, right? Gets to sort of the like, are people going to hate AI more and more? Yes, because now smartphones and PCs are not going to get incrementally better year on year. And in fact, they're going to get incrementally worse.
And if you look at the bill of materials of an iPhone, what fraction of it is the memory? Like how much more expensive does an iPhone get if the memory is 2x more expensive or whatever it has to be?
So I believe an iPhone has 12 gigabytes of memory. Yeah. Each gig used to cost roughly $3 or $4, so it's $50. But now the price of memory is like tripled. Let's call it, if it's now, it's $12 per gig for DDR. So now you're talking about $150 versus $50, right? $100 increase in cost on Apple. Also, Apple has some margin. They're not just going to eat the margin. So now that's a $100 cost increase. That's just on the DRAM. The NAND also has this same sort of like market. So in fact, it's probably a $150 increase on the iPhone. Apple has to either pass it on to the consumer, A, or B, they have to eat it. I don't see Apple reducing their margin too much. Maybe they eat a little bit. But at the end of the day, that means the end consumer is paying $250 more for an iPhone. And now that's on like, hey, what is last year's memory pricing versus today's? Now, there's some lag for Apple to have to feel the heat because they have tended to have, 3, 6, or a year-long contracts for a lot of memory. But at the end of the day, Apple gets hit pretty hard by this. But they won't really adjust until the next iPhone release. But that's the high end of the market. Actually, that's only a few hundred million phones a year, right? Apple sells, 200-300 million phones a year. The bulk of the market is this mid-range low end, right? Used to be 1.4 million smartphones were sold a year. Now we're at like 1.1. But our projections are we maybe get down to like 800 million this year. And next year, like 600 or 500 million. Because, and we look at like, there's some data points out of China from some of our analysts in Asia and Singapore and Hong Kong and Taiwan. They've been tracking this, and they see Xiaomi and Oppo are cutting low-end and mid-range smartphone volumes by half. Because yes, it's only a $150 price increase on a $1,000 smartphone, or $150 BOM increase on a $1,000 iPhone, where Apple has some larger margin. But if we look at the smaller phones, the percentage of the BOM that goes to memory and storage is much larger, and the margins are lower. So there's less capacity to even eat the margins, and they have like generally tended not to do as long-term agreements on memory. And why this is like a big deal is if smartphone volumes, let's say half, the halving will frankly happen in the low and mid-range, not in the high end. So it's not like the bits released are halving, right? Currently consumers more than half of memory demand. Even if you half the smartphone volumes because of the shape of the halving, right? It's like low end gets cut by more than half, high end gets cut by less than half, because you and I will buy, the high end phones that cost north of $1,000, we'll buy them, even if they get a little bit more expensive. And Apple's volumes will not go down as much as like a low end smartphone provider. And the same applies to PCs. And what this does to the market is quite drastic, right? DRAM gets released, goes to AI chips who are willing to do longer term contracts, willing to pay higher margins, et cetera, because at the end of the day, the margin that they extract is much larger from the end user or whatever. And so this probably leads to like people hating AI even more, right? Because they're going to start being like, today you already see all the memes like on like PC subreddits and PC like Twitter, gaming PC Twitter is like, cat dancing videos, and it's like, this is why memory prices is doubled and you can't get a new gaming GPU, right? Or you can't get a new desktop. And it's going to be even worse when memory prices double again, especially DRAM. Another dynamic that's quite interesting is it's not just DRAM, it's also NAND. NAND is also going up in price. Both of these markets have expanded capacity very slowly over the last few years. NAND almost zero, but smartphones, the percentage of NAND that goes to phones and PCs is larger than the percentage of DRAM that goes to phone and PC. So as you destroy demand, you unlock more, mostly for the DRAM purposes, you unlock more NAND that gets allocated and can sort of go to other markets. And so the price increases of DRAM will be larger than those of NAND because you've released more from the consumer. And in fact, you've produced more memory for AI.
Sorry, but the NAND is, I maybe just explained it and I missed it. Is it because SSDs are being used in large quantities for data centers, or?
They are, but not as large quantities as DRAM.
So, okay, but so you're saying they will also increase because they're using in some quantity, but like there's not as much in need as there is for HBM. Mm-hmm. Makes sense. One thing I didn't appreciate until I was reading some of your newsletters is that basically the same constraints that are preventing logic scaling over the next few years it's quite similar to what's preventing us from producing more memory wafers. In fact, like literally the same exact machine, this EUV tool is needed for memory. So I guess, yeah, maybe there's a question that somebody could be asking right now, like, well, why can't we just make more memory?
Is that somebody you?
Yeah, who knows?
So I think the constraints, as I was mentioning earlier, are not necessarily EUV tools today or to next year. They become that as we get to the latter part of the decade. But currently, right, the constraints are more so, they physically just haven't built fabs, right? So over the last 3 to 4 years, these vendors have just not built new fabs. That's because memory prices were really low, their margins were low, and in fact, they were losing money in 2023 on memory. So they're like, oh, we're not building new fabs. And then like the market slowly recovered over time, but never really got amazing until last year. In 2024, we were like banging on the drums that like, hey, reasoning means long context, which means large KV cache, which means you need a lot of memory demand. And we've been talking about that for like a year and a half, 2 years. And people who understand AI, like, went really long memory then, right? And so you've seen that sort of like dynamic, but now it finally played out in pricing. It took so long for what was obvious, right? Hey, long context, KV cache gets bigger, you need more memory, and accelerators, half their cost is memory. So of course they're just going to start, they're going to start like going crazy on it. It took a year for that to actually reflect in memory prices. Once memory prices reflected, then it took another 6 months, 3 months for the memory vendors to start building fabs. And those fabs take 2 years to build. And so we don't have really meaningful fabs that you can even put these tools in until late 27 or 28, right? And so instead what you've seen is like some really crazy stuff to get capacity, right? Micron bought a fab from a company in Taiwan that makes lagging edge chips, right? Hynix and Samsung are doing, some pretty crazy things to try and expand capacity at their existing fabs that also have like very large knock-on effects in the economy. And so, hey, why can't we build more capacity? Is like, there's nowhere to put the tools, right? And it's not just EUV. There's other tools involved in DRAM and logic, right? Like logic, N3, 30% or so of the cost, 28% of the cost is EUV of the wafer, of the final wafer. When you look at like DRAM, it's in the teens. And it's going up, but it's in the teens. So it's a much smaller percentage of the cost is DRAM or is EUV. These other tools are also bottlenecks, although their supply chains are not as complex as ASML's. Yeah. And so you see Applied Materials and Lam Research and all these other companies also expanding capacity a lot. And anyways, you don't have anywhere to put the tool because the most complex building that people make is fabs, and fabs take 2 years to build.
You can think of Jane Street as a research lab with a trading desk attached. Their infrastructure team has built some of the biggest research clusters in the world, with tens of thousands of high-end GPUs and hundreds of thousands of CPU cores and exabytes of storage. This compute is part of how Jane Street surfaces all the hidden patterns that are embedded in incredibly noisy market data. Even beyond the noise, the nature of the signal changes constantly in reaction to things like pandemics and elections and new regulations, and even changes in sentiment. What to do in years. London, New York, drops. /Thor plan is that I guess they're going to build this gigafab, terafab, some power of 10, and they're going to build the clean rooms. I won't even ask you about the dirty rooms thing, but like, let's say they build the clean rooms. I have a couple questions. One, do you think this is the kind of thing that Elon Co could build much faster than people are conventionally building it? Well, this is not about building the end tools. This is just about building the facility itself. How complicated is it to just build a clean room and do it extremely fast? Is it something that like Elon with his move fast thing could do much faster if that's what we're bottlenecked on this year or next year? And two, does that even matter if in 2 years your view is that we're not bottlenecked on clean room space, but we're bottlenecked on the tooling?
So I think as with any complex supply chain, it takes time and constraints shift over time.
Yeah.
And even if something isn't any longer a constraint, that doesn't mean that market no longer has margin, right? So for example, energy will not be a big bottleneck as we get to a couple years from now. But that doesn't mean energy is not growing super fast and there's no margin there. It's just like it's not the key bottleneck. And in the space of fabs, right, clean rooms are the biggest bottleneck this year and next year. And as we get over time, 28, 29, 30, there will be still constraints there. The thing about Elon is, I think he's had a tremendous capability to garner physical resources and really smart people to build things. And the way he's able to recruit really amazing people is just try and build the craziest stuff, right? In the case of AI, that's not really worked because everyone's trying to build AI. Everyone's very ambitious. But in the case of like, we're going to go to Mars, we're going to make rockets that land themselves, or we're going to make fully autonomous cars that are electric, right? Or we're going to make humanoid robots, right? Like these are methods of recruiting the people who think that's the most important problem in the world to work on that problem because he's the only one trying really hard. In the case of semiconductors, I want to make a fab that's 1 million wafers per month. No one has a fab that big. That's what he stated, right? He wants to make 1 million wafers a month. It's possible that he's able to recruit a lot of really awesome people and get them on this this crazy task of trying to build a fab that does 1 million wafers per month. Step one is to build a clean room. And I think that he probably can do, right? I think, there's some mindset, his mindset around like delete things, it can be dirty, it's fine. Probably not right. Or actually, I think 100% it's not right. You like need the fab to be very clean. I think all of the air in the fab gets replaced like every 3 seconds. It's like that fast, and there's so few particles per. But I think he can build the clean room. It'll take a year or two, maybe. Initially, it won't be super fast, but then over time, he'll get faster and faster at it. But then the really complex part is actually developing the process technology and building wafers, and I don't think he can develop that quickly.